Good morning, everyone. I am Vinita, working as an associate professor in the Department of Electrical and Electronics Engineering, RMD Engineering College. Today, I am going to explain a topic in Power System Transients, Unit 5, switching surges on an integrated system. So, all of you know the meaning of integrated system. If number of units connected together, that form a system is called integrated system. So, in this integrated, let us see how the switching surges that affect the power system. Let us see the definition for this integrated switching surges on an integrated system. The disturbance produced by the switching operation in a system spreads out throughout the integrated system by setting up traveling waves. They travel along the connected lines and reflect to and from as discontinuities are encountered. So, in the fourth unit, we have studied about the traveling waves. So, whenever any switching contacts get opened, the voltage and current that will be moved from one point to another point, that is from one termination to another termination by means of a traveling waves. So that traveling waves, whenever that start from one end and that will reach another end, there will be a there will be a reflection as well as the refraction. Okay, so in order to study the effects of this reflection and refraction, we can consider a system which will have two buses, 138 kV and 345 kV, interconnected by means of an auto transformer. Here we can see the system. So 345 kV and 138 kV buses both will be integrated. That is, this 345 kV and 138 kV that is connected by means of an three-phase auto transformer, and this 138 kV that is connected by means of a generator transformer system. And here, the number of lines that will be connected to 345 kV as well as 138 kV buses. The third circuit that represents the equivalent circuit of the second circuit diagram. So here I have explained 138 kV bus, which is fed through the generator transformer unit, and the transmission lines are connected to both the buses. And the third circuit is nothing but an equivalent circuit. In that circuit, the lines are represented by the resistors R1 and R2. And the purpose of providing the resistance R1 is to suppress the oscillations. Whenever the switching contacts get open, obviously due to the presence of inductance and capacitance, oscillations will be produced in the circuit. So in order to reduce the oscillations, the resistance R1 that will be provided in the circuit. And here, these are the switching values for the capacitance as well as the inductance of the same circuit. So this is regarding 345 kV circuit. For this 345 kV circuit, the value of C1 is 0.025 microfarad and L1 is 0.11 Henry and C2 is 0.32 microfarad. Corresponding L2 is 0.11 Henry and C3 is 0.06 microfarad and L3 is 0.04 Henry. And the value of R1 that is equal to 80 ohms and R2 that is equal to 670 ohms. And here the representations for the capacitance and inductance are given. C1 is the capacitance of 345 kV bus. C2 is the capacitance of 138 kV bus. C3 is the capacitance of generator bus. Similarly, L1 is the inductance of auto transformer. L2 is the inductance of generator transformer unit. And L3 is the generator inductance. And R1 and R2 are the parallel surge impedance of the transmission lines. And here, the surge impedance that will be calculated using this formula, square root of L1 divided by C1. So already here, we have the values, that is the design values are specified for this 345 kV lines. It is 0.11 Henry and 0.025 microhenry. So if you calculate the value for L1 and C1, it is the surge impedance. that is equal to 21,008 ohms. So if you compare the resistance value of 80 ohms, the surge impedance value, that will be very, very high value. So the 80 ohms of 345 kV lines, which is much lower than this value. So what will happen is it will be over damping the circuit. The source circuit can be replaced with little error by a parallel load resistance circuit in which L is equal to L1 plus L2 plus L3 and R is equal to R1. From this, we can calculate the response of this parallel RL circuit with a ramp input of I of t, which is given by V of S, that is equal to R into I naught divided by S into S plus R by L. And here from this, we can take inverse Laplace transform. If you take and calculate in time function, we'll be getting V of t, that is equal to L into I naught into 1 minus e power minus R by L into t. This is the value of voltage for the parallel RL circuit. And here, that is, if you draw the characteristics, and from the characteristics, if you take the slope and if you calculate the value for I naught, we'll be getting the ratio as I naught is equal to Vp by L. From this, we can calculate the magnitude of I naught, where Vp is the peak system voltage. Now here, for the same system, that is, we can analyze this topic by means of taking an hypothetical system. Okay, so in this system, all the stations are represented by various stones like diamond, emerald, ruby, topaz, sapphire, etc. And this is the starting station. At this station, the fault has been occurred. And from this diamond station, number of stations that will be connected. So emerald, ruby, topaz, sapphire, number of stations that will be connected. And here, the distance between the two stations that will be specified in miles. So the distance between diamond and emerald is given by 62 miles, and the distance between diamond and ruby is given by 48 miles, and the distance between diamond and topaz is given by 15 miles. And here there are two lines are there. So what does these two lines represent? It is nothing but a double circuit line. And moreover, from each and every station, the waves that will be, that is, for example, if it is an voltage wave, means it will be traveling from one station to another station. So there will be no reflection from this emerald station. Only there is a refraction. But if you take this topaz station, there is an input voltage from this diamond and it will reach the topaz. And again, from the topaz, there will be a reflecting wave that will reach the diamond. So here there will be a reflection as well as the refraction of the traveling waves takes place. And here each of circles already I have explained. So each of the circles named for some precious stone that represents the station. So the lines between the stations are called as tie circuits. And here, for each and every cycle, or we'll call as an for a single cycle, the time duration that will be taken is 10.8 microseconds. This is per round trip mile, that is for a single round. So it will, the wave, if it starts from one end and again that will reach its another end, again that is, it is traveling and again it will be reaching the same end. For that, the time taken is nothing but 10.8 microsecond. And for this, we can calculate the value of V of t. V of t already we have derived Vp into 1 minus e power minus R by L into t. So what is R by L? R by L is nothing but alpha. And here we have to calculate the value of this R by L. And if you substitute the value of R by L in this equation, we can calculate the magnitude of the voltage wave. Here, if you calculate the value of L by R, So already we have given the value of L by R. It is 0.22 divided by 80 for a 345 kV line. So if we calculate, it becomes 2.75 into 10 power minus 3 seconds. And we need to substitute the value of L by R in the previous expression. So V of t is equal to Vp into 1 minus e power minus, here it is given as R by L. But we have calculated the ratio as L by R. So depends upon that, we have to substitute the inverse value here. And so we can calculate the value of V of t. So V of t, that is equal to Vp into 1 minus e power minus 364 t. And here the waveforms are drawn for the input of RAM current, for capacitance neglected as well as the presence of capacitance. In the first waveform, it is drawn between voltage as well as time period without adding the value of capacitance, so that it will be starting from zero. But in the second case, the effect of capacitance that will be included in the circuit. If the capacitance effect is included, obviously what will happen? There is a time period, that is, there is a time constant between the zero as well as the operation of the circuit breaker. So that is shown in this diagram here. This is the small time period after which the waveform that has been started. So this is due to the effect of capacitance. Now here, for this case, we can calculate the value of magnitude of the reflected wave as well as the refracted wave. Already in the fourth unit, we have studied the formula to calculate the reflected wave. So it is represented by VR. VR is equal to A into VI. VI into this can be written as VI into the value of A can be substituted here, Z2 minus Z1 divided by Z1 plus Z2, where VI is the incident wave and Z2 is the impedance of the station having encountered, and Z1 is the impedance of the line among which the incident wave is advancing. And from this, we can calculate the value of VI of S. VI of S, that is equal to Vp by R into I naught divided by S into S plus R by L. And here we have given the final expression for the input voltage VI of S. And from this, we can calculate the reflection coefficient A of S. So if you calculate the reflection coefficient after substituting the value of Z2 of S, the value of, that is the equation for A of S, that is equal to R by R plus Z1 minus S divided by S plus Z1 into R by L into R plus Z1 minus Z1 divided by L into R plus Z1 minus R plus LS divided by S plus Z1 into R by L into R plus Z1. And similar to the reflection coefficient, we can calculate the value of refraction coefficient. This refraction coefficient can be so from after calculating the value of A of S, we can calculate the reflection coefficient A of S, that is equal to R minus Z1 divided by R plus Z1 into S divided by S plus beta minus B divided by S plus beta. And here the incident wave VI of S can be represented by Vp by Vp into 1 divided by S into S plus beta. We need to substitute the value of beta, and this is your final expression. Therefore, the magnitude of the reflected wave can be written as Vp into R minus Z1 divided by R plus Z1 into 1 by S plus alpha into S plus beta minus beta divided by S into S plus alpha into S plus beta. So all those things we have studied in fourth unit. Now the transmitted and the refracted wave at such an encounter can be determined like the previous. That is, we have calculated the reflected wave. Similar to that manner, we can calculate the value of refracted wave. So Vi is equal to B into Vi, where B is the refraction coefficient. This can be written as 2 into Z2 divided by Z1 plus Z2. And here that is the refraction coefficient B of S can be written as 2 into R divided by R plus Z1 into S divided by S plus beta. So like the previous case, here also we can calculate the value of Bi of S. Then after that we have to take inverse Laplace transform to find the final expression for Vi of S. So here they have calculated the L inverse value, and from that we can calculate the value of Vt of S. So by in this derivation, we have discussed about how the traveling waves will be propagating from one station to another station, and here we have calculated the magnitude of reflected as well as the refracted waves. Thank you.